Hi, I'm Kirk Weiler, and today we're going to be looking at numerical and calculator derivatives in Math 4 Honors. After two pretty tough lessons for my students in a row, we did implicit derivatives one day, and then we followed it up by differentiability the next day. We're going to be looking, I think, at a topic that's pretty easy. Now, let me kind of give you the background on this. So, we're really looking at two things, numerical derivatives and calculator derivatives, and they're very similar. They're linked together. But the AP exam and general mathematics would like you to be able to handle functions in three different forms. Sometimes this is referred to as the rule of three, so to speak. And the rule of three says you should be able to deal with functions. Where's my pen there? You should be able to deal with functions sort of in equation form. You should be able to deal with them in graphical form. And you should be able to deal with them in table form or tabular form, either way. I'll just say table form. So today, or at least on the front side of the worksheet, we're going to be dealing with functions that are defined using tables. And tables are really awesome because immediately you can see outputs for inputs. I mean, just kind of glancing at exercise 1, I could immediately say that when the input is 3, the output to my function is 8. But of course the problem with tables is that they lack a lot of information. We don't really know what's going on between any two x values. We know sort of what's going on average, but we don't know what's going on, sort of in specific details. So let's take a look at how we can use data in tables to approximate derivatives. Exercise 1 says the function f of x is continuous and differentiable. And it should say for all values of x. It just says or all values of x. That's kind of interesting. I can't really correct it right now for some reason, but that should be for all values of x. And it says give an approximation for the value of f prime of 2, and then we need to show the calculation that leads to our answer. Alright, what I'd like you to do right now is pause the video for maybe a minute and think about just what is the derivative? What is f prime of 2? And then, how can you use the data in the table to take your best shot at what the derivative is at f prime of 2, your best approximation? Pause the video now. Alright, let's come back to it. So, as we all know, the derivative, f prime of 2, is the slope of the curve at that point. Now, I don't exactly know, in fact, I don't know really much at all about what this function looks like, right? I've just got these sort of spot values, right? At -1, I know it's at -3. At 0, I know it's at -1. At 1, I know that it's 2. But I really don't know much else that's going on. At 2, I know that it's 3. At 3, I know that it's way up here at 8. I'm not going to even try to draw that out. But I don't know if it's a cubic. I don't know if it's doing crazy stuff between the points. And what I want to do is I want to try to approximate the slope of the tangent line at x equals 2. I don't even know if this is the right way for the tangent line to look. For all I know that the curve is actually decreasing there. I really don't know. But what we should know is that it's a slope. And if we're going to approximate the derivative using information that we have, then it sort of makes sense to calculate a slope. Now there's sort of three acceptable slopes that are approximations for f prime of 2. To me, the most logical one is to calculate the average rate of change for, actually let me get rid of that, I apologize. I'd like to calculate the average rate of change for the two x values, or between the two x values, that are closest to 2. In other words, I would say that f prime of 2 would be approximately f of 3 minus f of 1 divided by 3 minus 1. So in other words, I can say that that's 8 minus 2 divided by 2, right? 3 minus 1, I'd get 6 divided by 2, and that would give me a derivative that was approximately 3. To me, that makes the most sense. It's sort of like going to these 2 points, drawing a secant line through them, and saying the slope of that secant line will be about the slope of the tangent line. Alright, that's why we're using the approximation symbol. It's actually also acceptable to use x equals 2 in this approximation. So it would also be okay to do something like this. F of 2 minus f of 1 divided by 2 minus 1. Then we'd have 3 minus 2 divided by 1. That would give us f prime of 2 approximately 1. Quite different, right? We could also say that f prime of 2 would be approximately f of 3 minus f of 2 divided by 3 minus 2. All of these would really be acceptable ways of approximating the slope of the tangent line at x equals 2. Now, one thing that we wouldn't know, though, is which one is the most accurate, or even how accurate it is. And that's why, or better yet, that's what motivates the question in exercise 2. Exercise 2 says, why is it critically important to use the approximation sign, right? Now, you may have used the approximation sign, this thing, for all sorts of different reasons. You may have rounded answers and said, oh, my actual answer is 5.3, but that's approximately 5. And that would be a correct use of the approximation symbol. But what I like about the approximation symbol is it really tells us that we don't know, right? So f prime of 2 is approximately 1, but honestly, I don't know what it is. And that's really the answer to number 2. We don't know what f prime of 2 is. That's not to say that f prime of 2 isn't exactly 3, as this answer would suggest, or 1, as this answer would suggest. Obviously, it can't be both of them. But we don't know. So we use the approximation symbol to really get at that idea. I'm just going to really quickly pause the video as my phone is ringing. Alright, we're back at it. Seriously, I don't know how I ever find 20 minutes to work through one of these videos without being interrupted in one way or another. Anyhow, so whenever we use a table to approximate a derivative, it is absolutely critical that we use the approximation symbol. For those students who are preparing for the AP exam, the conventional wisdom is if you don't use the approximation symbol, you'll be docked some amount of credit because you're making the claim that you know for certain that the derivative is the following value. But you'll never know that from a table. So take a look at exercise 3. Here we have an applied problem. Why don't you read it over? Hit pause on the video and try to give an approximation for the derivative that they ask for. Hit pause now. Alright, let's take a look. So here we've got actually a nice applied problem where we've got the volume of water in a tank, given in gallons, as a function of the input, which is time, given in minutes. It says selected values of the differentiable function v are shown in the table below. Just a little comment. When you see a comment that says that a function is differentiable, what that means is that its derivative exists everywhere within the domain of the function. So it says using this data, give an approximation for a dv dt at t equals 30 minutes. Alright, so we want to try to figure out an approximation of the derivative of the function right there, and we want to include units in our answer. So I'm going to say that dv dt, or v prime of t, depends on how you want to put it, is approximately, and again I'm going to stick with this, I'm going to say that it's v of 40 minus v of 20 divided by 40 minus 20. You will get a different answer if you include the 30. So if you do 30 and 40, or 20 and 30, you'll get a different answer. But if I do v of 40 minus v of 20, obviously v of 40 is 240. V of 20 is 310. Make sure you do the subtraction in the right order. I'm going to do this subtraction right now, 20. And simplify this down, we get negative 3.5. Hopefully you've had some discussions so far about the units that derivatives can have. The beautiful thing about the units of the derivative is that all you have to do is keep track of the units of the numerator. That's 240 gallons minus 310 gallons, so that's gallons, divided by the units of the denominator, 40 minutes minus 20 minutes, gives us minutes. So the derivative is approximately negative 3.5 gallons per minute. Now you may take issue with something. You might say, hey, wait a second, you used the equality symbol there. Shouldn't you use the approximation symbol? And I would say, no, not at all. I'm a strict believer in what this symbol means, right? And this symbol means that the thing on this side and the thing on this side are the same, and they are. And the thing on this side and the thing on this side are the same, and they are. But what I can't say for certain is whether dV dt is identically equal to negative 3.5 gallons per minute. But it is a little bit confusing when you use one symbol versus the other. So let's keep going. Now, that's about it. All right, that's about it. The second part of this lesson, what we're going to do is we're going to look at how we can use our calculator, specifically how to use a Texas Instruments graphing calculator, either an 83 or an 84, plus or non, doesn't really matter, in order to find the derivative of a function at a given point. If your teacher never told you this existed, that's probably because they didn't necessarily want you to know about it until it was time. Your calculators, if you've got the 83 or the 84, can tell you what the slope of the tangent line is at any value of x. Now, unless you have a much higher version of a calculator, like the Texas Instruments 89, you cannot actually find out that the derivative of x squared is 2x. You can't figure out the derivative formula. You can only find the value of the derivative at a particular value of x. So in exercise 4, what we're going to use is we're going to use the graphing calculator to find the derivative of a very strange function, y equals x to the x at x equals 2. Now this is not a power function, nor is it an exponential function. Don't get me wrong, at this point in time, my students don't know how to find the derivative of an exponential function, so that wouldn't help anyway. But you certainly can't use the power rule on this. So what I'm going to do is I'm going to actually exit the program I'm in right now. I'm going to start up my graphing calculator, and I'm going to show you how to use the nDerivative command to find a numerical derivative. So we're opening up the TI Smart View for the TI-84 Plus. Now remember, I'm trying to find the derivative of y equals x to the x at x equals 2. This always takes a little while to open up. Come on, TI Smart View, you can do it. Here it comes. Alright, I'm going to hide some things because I don't need them. I'm going to register later. Sure I am. Sure I am. Right, and here's my calculator. Let me get it down into the screen where you can view it. Alright, let's talk about where you can find the numerical derivative command, also known as nDerivative. Just for right now, I'm going to go back to my main screen. Alright, I'm on my main screen of the TI-84 Plus, and I'm going to go into the Math button. Alright, I'm going to hit Math, and I'm actually going to go down my list until I find Math option 8. That's nDerivative, and then I'm just going to hit Enter. What that does is it puts me out onto the main screen. What I next do is I enter in the function I want to find the derivative of, x raised to the x. I then, and this is very strange, have to tell it what the independent variable is. I'm going to let it know that the independent variable is x, and then I'm going to tell it the value at which I want it to find the derivative. So again, you're going to put in nDerivative, which you find by going to the Math option 8. You're going to put the function in here without y equals. You're going to put in the variable here. For right now, that's always going to be x. And then you're going to put the value here that you want to find the derivative of. As soon as you now hit enter on your calculator, it gives you an approximation for the slope of the tangent line, 6.77259, etc. Now, on the AP, the standard is to give 3 decimal places of accuracy. Now, I'm going to write something down that's absolutely crazy right now. I'm going to say dy dx is 6.773, and I'm going to use the equality symbol. I'm not going to use the approximation symbol, and let me explain why. Alright, the numerical derivative command on your calculator does exactly what you'd think it would do. Now, I don't exactly know what x to the x looks like. It's a crazy function. It grows extremely fast. I'm going to draw it as if it kind of looks like y equals x squared, which is not too bad. What the numerical derivative command does on the graphing calculator is it picks 2 values of x that are exceptionally close to 2. I'm not talking 1 and 3. I'm talking 1.9999999, 2.0000001, and it calculates the average rate of change, and it does it even better than this. but you can kind of get the idea. It probably does something like 2.0001 minus f of 1.9999, and again, it's actually much more accurate than this. I'm just doing kind of an approximation here. So your calculator is doing this, and it's, for the most part, getting a very, very accurate description of the slope. So accurate that we can actually say it's accurate to 3 decimal places. We don't need the approximation symbol here. On the front side of the sheet, we need the approximation symbol because, quite frankly, I don't know how accurate those derivative approximations are. Here, the derivative approximation is excellent. All right, let's do what I call a confidence building exercise. Sometimes I don't really like it when I just use technology to find answers for me because I don't really trust it, and quite frankly, I don't really know how to find the derivative of x to the x anyway. Well, actually I do, but you don't know how to find the derivative of x to the x. Not likely. Not yet. So let's do one that we do know how to find the derivative of. Let's find the derivative of f of x equals 3x squared minus 1 quantity to the third at x equals 1. Let's do it using the chain rule. Then let's do it using the numerical derivative command on our calculator. Pause the video right now and find the derivative f prime of 1 using the chain rule. When you're ready to unpause the video, you could either then try to do the numerical derivative command on your calculator, or I'll show you how to do it one more time. I'm going to show you how to do it one more time anyway, but if you think you know how to do it at this point, try it on your own. Alright, pause the video now. Okay, let's do it. Let's first find this derivative algebraically. So we're going to do the chain rule, and remember how the chain rule works. We've got this inner function, 3x squared minus 1. We have an outer function, the cubing function. So I'm going to ignore the inner function. I'm going to take the derivative of the outer function. That's 3 times the inner function squared. I'll just kind of fill that in second, just to make sure I don't do anything weird. Then I'm going to multiply it by the derivative of the inner function, 6x. If you want to, you could clean this up and make it into 18x times 3x squared minus 1, quantity squared. So if I want f prime of 1 now, I can just substitute 1 in. So I'll get 18 times 1 times 3 minus 1 squared. And if you work out all the numbers on that, you find that there's a slope of 72. All right, now, little confidence building exercise. Let's go over to the TI-84 and let's make sure that it will get the same answer. All right, so let's go to math. We're going to go down to option 8. You can just hit 8 right now. Whoops. But, you know, for you, I'm going to overshoot it. So I'm going to hit enter. I'm going to put in my function. Now I have to be kind of careful about my parentheses, but I'll have 3x squared minus 1 quantity to the third. Right? So I put in my function first. Then I'm going to actually have to tell it that x is the independent variable. I know that seems silly, but remember, this is a computer. It's not very smart. It's really just running a subroutine. Right, so for those of you that have some programming experience, it's just running a little subroutine. It's saying, hey, take this function, take this value, let this thing go a little bit above and a little bit below, and then calculate the average rate of change. Let's see how accurate it is. Pretty good, right? Pretty good. In fact, right, we can say that the numerical derivative command gave it to us as 72.000432. It is off a little bit. We shouldn't really have that, but it is accurate to 3 decimal places. Now, the larger the slope, the more likely that the numerical derivative command could actually be off, not by a significant percent, but by little bits here and there. Now, the one word of caution about numerical derivatives on the calculator is that the calculator, again, is not very smart, right? All it's doing is taking the function that you give it, it's taking the x value you give it, it's going a minute amount to the right, a minute amount to the left, and then calculating the average rate of change between the two, which gives you a very good sense for what the instantaneous rate of change, i.e. the derivative, is doing. All right, but let's take a look at 2 situations where the calculator messes it up big time. All right, take a look at exercise number 6. We've got the function y equals absolute value of x and the function y equals 1 over x. And I ask you to explain why both of these functions fail to be differentiable at x equals 0. And it's for different reasons. So pause the video right now and think about the lesson that you've seen on differentiability and why these two functions both fail to have a derivative at x equals 0. Totally different reasons for both. Did you figure it out? So y equals the absolute value of x fails to have a derivative at x equals 0 because it's got a corner there, right? A sudden change in the slope, producing a corner, and no derivative, right? On the other hand, 1 over x doesn't have a corner at x equals 0. In fact, it doesn't have anything at all at x equals 0, right? It's discontinuous there. It does have a vertical tangent line, a vertical asymptote, but the plain fact is it's not continuous at x equals 0. So neither one of these should have a value for dy dx at x equals 0. The freakish thing is that the calculator gives us a value for dy dx at x equals 0 for both of these. So what I'd like you to do is I'd like you to pause the video right now, use your calculator with the n derivative command or whatever command your calculator has on it, and see what it gives you for these two functions in terms of their derivatives. I'm going to lay it out like this. Y equals absolute value of x and dy dx at x equals 0 and y equals 1 over x. Let's see what the calculator tells us there for dy dx when x is 0. Again, if the calculator was smart, it would say in both situations that the derivative doesn't exist. But it's just not that intelligent. So pause the video for a second and see what your calculator gives you for these derivatives. Alright, let's take a look. This will give us a chance one more time to look at how to use the calculator to find these numerical derivatives. I'm going to just clear the home screen. I'm going to go to Math. I'm going to go to option 8. By now I know it's option 8. What's beautiful is if I do that, then it just immediately takes me back out to the home screen. I'm going to go to Math. I'm going to go over to the number so that I grab absolute value, right? Absolute value of x, comma, x, comma, 0. Alright, remember, if the calculator's smart, it says to us, you're crazy, man. I got a corner there. I can't find the derivative. But it tells us the derivative is 0. Whew, that is so wrong. It's so wrong. Let's go back to here. Right? It tells us that the derivative is 0, and this is wrong. The derivative does not exist at a corner. Alright, let's do it for 1 over x. Now, for 1 over x, I bet many of us will have answers that differ. Let's do Math, option 8. We'll do 1 divided by x, comma, x, comma, 0. Now again, remember, it should say to us, sorry, no can do, discontinuity there. And look at that. That's a lot of zeros. You know what's kind of cool about my answer is it's a million, right on the money. A million, right on the money. So let's write that down. And again, that's really, really wrong. So I really want to emphasize this. I'm going to put the commas in so you can really understand how big this is. And again, this is as wrong can be. The calculator is just not very smart. The beautiful thing is if you understand derivatives, if you understand how they were developed, if you understand what the calculator technology is doing, both of these answers make all the sense in the world. Remember, what the calculator is doing is it's taking the value of x that you give it, it's going slightly to the right and slightly to the left, the same amount by the way, it's going symmetrically to the right and the left, and it's then finding the slope of the secant line. So I'm gonna just change to a different color, right? So if you actually looked at y equals root x and pretend I really just, magnified this. What the calculator is doing is it's taking a value to the right of x equals 0 and to the left of x equals 0, and it's calculating, beautifully done, Weiler, it's calculating the slope of that secant line, which is clearly 0, even though the slope of the tangent line here doesn't exist. With y equals 1 over x, what it's doing is it's picking a point down here, it's picking a point way up here, and it's calculating the slope of that line, which is really large. right? Really, really large. And again, it kind of makes sense because it's probably going just a little bit to the right and getting a huge y value, going to the little bit to the left, getting a huge negative y value, and then calculating their slope. So I guess at the end of the day, one thing that you want to note is that you have to be aware of technology. And the best way to be wary of technology is to understand what the technology is doing, or better yet, how it's doing it. All right, we're going to stop there at this point. Thank you for joining me as usual. Until next time, remember, don't get into a staring contest with a llama because they spit. Take care, everybody.